we will try to study the new concept of moment of inertia. Moment of inertia of a section is defined as the product of area of a section and square of distance between the centroid of section and reference axis. It is also called a second moment of area, which is resistance to bending, and this property of moment of inertia is used in designing of various machine parts in mechanical engineering and in designing of structure in civil engineering. Now let us try to understand what is moment of inertia. We do have a theoretical definition of it. Moment and inertia, these are the two words, when clubbed together form moment of inertia. We know moment. Moment is force into perpendicular distance between point of application of force and axis of rotation. Mathematically, m is equal to F into d, where m is moment, F is force, and d is the perpendicular distance. So basically, it is a moment which is being produced because of external loading on a beam. I repeat, moment which is being produced because of external loading on a beam. Let's come to meaning of inertia. We have studied in physics Newton's law, which says that inertia is the tendency of a body to maintain its state of rest or that of uniform motion. So, if a body is in rest, it will try to remain in rest. So here, moment of inertia, when we club the two words together, what it means is that it is an inertia that is a resistance to the moment. So whatever external moment that is being on a beam which causes bending action, so to this bending action the beam will resist. The beam's material inherent property will try to resist this moment. That's why it is also called as second moment of area, which is resistance to bending. This mechanical property of any material is very useful in various fields, and that's why we have to study moment of inertia, so that we need to know moment of inertia of various sizes, shapes for its future application. Next slide. Now in this diagram I have drawn, we have a simply supported beam. AB is a simply supported beam on which external loading UDL, that is uniform distributed load, is there. Its cross section is rectangular section with width B and depth D. Because of uniform distributed load, there is a bending moment on the beam. So you can see slightly the beam is bent in figure B. Now this bending moment is externally. Internally, the beam will try to resist this bending action. This internal resistance of the beam to the external bending action is known as moment of inertia. This resistance to moment is known as moment of inertia. Dear student, I hope you had a fair idea about what moment of inertia is. Things will gradually get more clear when we solve numerical. Now we move to next slide. The unit of moment of inertia is mm raised to 4. Now this diagram again very familiar to you. We have again studied the same diagram in applied mechanics. Now the same diagram is repeated over here. We have axis OA and OB, irregular section of or diagram, a regular figure by which we have named it as A, small elementary bodies A1, A2, A3, A4, and its respective distance with OA and OB. So this is the same diagram. Now we will try to look at its mathematical formula in the next slide. The mathematical expression or formula for moment of inertia about its OA axis and OB axis. So this mathematical formula is with reference to the diagram which we have just studied. IOB, that is moment of inertia about axis OB, that is axis which we have seen in the diagram, is A1 y1 square plus A2 y2 square plus A3 y3 square and so on till AN yn square, which can be written as IOB is equal to summation area y square. Similarly, IOA can be written as equal to IOA is equal to A1 x1 square plus A2 x2 square plus A3 x3 square and so on till AN xn square, which can be written as IOA is equal to summation A x square. Next slide. Where IOA is moment about OA axis, IOB moment of inertia about OB axis. Capital A, area of lamina, that is the irregular section which has been shown. Capital Y is equal to distance of centroid from OB axis, X, distance of centroid from OA axis, A1, A2, A3 till AN, elementary area of lamina, small elementary area. This all area, when we add all this area, we get the total area of the lamina, that is A. So A1 plus A2 plus A3 and so on till AN, we get the complete area. X1, X2, X3 and so on till Xn is distance of centroid of respective elementary area from OA axis. We have seen it in the diagram that OA, its distance from OA axis is x1. Similarly, y1, y2, y3 and so on is equal to distance of centroid of respective elementary area from OB axis. Now we'll move to the next slide. Again, we'll study a new term. Now, this lecture is more of theory in nature. This lecture consists more of theoretical part. So, we will first cover a few simple concepts. We will try to explain, understand it, and again we will revise it, repeat in when we try to solve the numerical. Radius of gyration, denoted by K, is defined as the distance at which the area A is supposed to be concentrated to give the same moment of inertia. Mathematically, I, that is moment of inertia, is equal to A into K square. Here K is radius of gyration. So in previous moment of inertia, where we have a into y square or x square. So x, instead of x or y, it is represented by k. K can be written as k is equal to under root I divided by a, or kxx is equal to under root ixx divided by a, or kyy is equal to under root iyy divided by a. Next slide. Where I is equal to moment of inertia about the axis considered, a area of section, k radius of gyration about axis considered. Unit of k is mm, millimeter, cm, centimeter, m, meter. Next slide. Now, before I go with slide, I repeat that a basic theoretical part we are covering, and we'll try to explain and go into deep into we will more be elaborate when we try to solve the numerical. So even if you don't understand, don't panic, don't worry, we will cover it. We'll repeat this concept again while solving numerical. Now, section of modulus denoted by Z. It is defined as section of modulus denoted by Z. It is defined as the ratio of moment of inertia about the neutral axis to the distance between neutral axis and the extreme layer of the section is termed as section modulus or modulus of section. Z is equal to I divided by Y max, where Z is equal to section of modulus, whereas I is equal to moment of inertia about neutral axis passing through the centroid of section. Y is equal to distance of neutral axis to the extreme layer of section. Now here, curiosity will arise that what is neutral axis. Now if we take a rectangular section and if we take the center of gravity of that rectangular section or centroid of it, when we cut it into half in x direction or horizontally or in y direction vertically, okay, it is at the midpoint of the complete section. So let's say if you take it xx, that is half of it, that is the neutral axis. Diagrammatically, we'll learn this in next in later slide. I hope it is clear to you. Fine. We will revise this theory part whenever we try to solve this numerical. Next slide.